Now we're going to look at matrices in this video, and basically all that a matrix is a way that we can write our numbers in a series of rows and columns. And an example we have here is 1, -4, 7, 2, 0, 3, 6, -1, and 9. And we're going to look at how we can eventually transform our linear system of equations into a matrix, which will make it easier to solve our systems of equations that we did in the previous videos. So let's look at setting up kind of the entries of our matrix. If you look here, we have down the side, we have row 1, row 2, all the way down until we have row M. And then going across the top, we have column 1, column 2, column 3, all the way over to column sub n. And here we just are identifying the entries A11, which means we're talking about row 1, column 1. A12, this is the entry that would be in row 1, column 2. So for example, here where we have A11, row 1, column 1, if we applied that to the example above, that would be the number 1. And if we were to look at A12, which means row 1, column 2, well, here we have row 1, column 2, that would be the number -4. And then we would have A13, which is row 1, column 3. And the example we have, that would be the number 7. Now, your matrix could continue. It can be more than 3. It could have any number of entries. So that's why here, this is going across to A1n. The letter n is representing the total number of columns. So the example above, there's a total of 3 columns. And then, of course, if we see A21, that says we're looking at row 2, column 1. A22, that means it's row 2, column 2, all the way over to A2, column sub n. And then, of course, we could go all the way to the bottom where we would have A sub m, which that's telling us the number of rows, the max number of rows in column 1. And then over here at the far bottom right, A sub mn, that's just representing the mth row in the nth column. So for example, that would apply to the number 9 in our example. For example, here we have AMN, that would be 9 here, which for this example would be A33 because we're looking at row 3 and column 3. Okay? Now, if we look at this specifically, we would identify this as the order of our matrix, and we're going to identify that by the row, which is m by n, where n is the number of columns. So the order of your matrix in this case is called a m by n matrix. So for the example that's given to us here, we would have 3 rows by 3 columns. So this would be a 3 by 3 matrix. And specifically here, when the rows and the columns are equal, in other words, when m equals n, the number of rows equals the number of columns, then you have what's called a square matrix, and I think that's for obvious reasons. So what happens if I give you the following example? If I was to give you, let's say, 1, 4, 8, and let's say 7, 0, -3. And if I want to know what is the order for this matrix, well, we would look and we would say, well, here we have 1, 2, 2 rows, so that would be 2 by 1, 2, 3 columns. So the order would be a 2 by 3 matrix. So that's just telling you basically the size of your matrix. All right, let's look at an example how we can transform a systems of equation into a matrix. And here we're going to look at two different types. The first matrix we're going to look at is what's called an augmented matrix. So here we have our system, x minus 3y plus z equals 1. And notice there's no x or z, so all we have then for the second equation is 4y equals 0, and the last equation is simply 7z equals negative 5. And we want to transform this into what's called an augmented matrix. And basically that means we're going to bring down the coefficients. So if we look at the first equation, the coefficient of the x, the y, and the z would be 1, negative 3, and a positive 1. So we bring down 1, negative 3, 1, and then a lot of times you'll have like a dotted line here, and then you're going to list your constant term, what it's equal to, which is 1. And then we go to the second equation. There's no x, so that's a 0. There's no z, so we would have 0, 4, 0, and our constant is also 0. And the last equation, we have 0x, so 0y, so that's simply going to be 0, 0, 7, negative 5. And of course, you want to make sure that you have your variables lined up like we do up here, where we have x's here is representing your first column, then your y's are in the second, and then of course the z's, and then where it's equal to would be your constant terms here as 1, 0, negative 5. So that's how we can write this system of equations as an augmented matrix. And then sometimes you'll hear something referred to as the coefficient matrix, and it's basically the same thing, but all we're going to do is list the coefficients. So in other words, we're going to leave out the constants here of 1, 0, negative 5, and we would simply have 1, negative 3, 1, 0, 4, 0, and 0, 0, 7. Now, what if I was to give you, let's say, a matrix? Let me see if I make up a matrix here. Let's say that we had 4, 7, 8, negative 1. And let's say that we had then negative 2, 0, 3, 8, 1, 4, 0, and 7. So if this is our matrix, this is the augmented matrix, and we want to write the equation, the system of equations for this matrix. So now we want to go the other direction. Given this matrix, we want to rewrite it as our system of equations. Well, then we're going to write this then simply as 4x plus 7y plus 8z equals negative 1, negative 2x. Now notice here there's a 0, so that would mean 0y, and then you'd have a positive 3z equals 8, 1x plus 4y, and then there's 0, so that means there's no z, equals 7. So that's what we have if we were to translate this matrix back to a system of equations. So hopefully now you have a little bit of understanding of as far as your matrix, and the next video we will look at how we can use our matrix to solve our linear system.